In this video, we're going to discuss the distribution of microstates for various macrostates for a system of two Einstein solids that are connected. The equation in the top right is the equation for the multiplicity of states, which is based on Q, the total number of units of energy that the two Einstein solids share, N, the number of particles in each Einstein solid, or the number of oscillators in each Einstein solid, and X, the difference between the energy of the system and the most likely macrostate of the system. So the most likely macrostate of this system is when each Einstein solid has exactly half the number of units of energy, and X is the difference between that value and the true value of QA and QB. So QA equals Q over 2 plus X, and QB equals Q over 2 minus X. So when X equals 0, each oscillator has half of the energy, and we are in the most likely macrostate. As X increases, A gains energy, and the number of microstates available to the system drops. And this graph tells us how quickly the number of microstates available to the system drops as our energy of QA increases. One thing to note about this system is that we are in the high temperature limit. That is, this equation, which is Schroeder 2.27, was derived in the under the assumption that Q is much larger than N, that we have much more energy than the number of oscillators in our system. And this distribution deals with the number of microstates, and therefore deals with the most likely place that we are or the most likely distribution of energy within the system when it is in thermal equilibrium. So this tells us if we are in thermal equilibrium, if the two Einstein solids have been able to trade energy back and forth such that they come to the same temperature, and we look at that system, how likely are we to find it in, say, a 50-50 energy split, or with slightly more energy in QA, or in Einstein solid A versus Einstein solid B, etc. Now, the first thing to note about this multiplicity function is that the multiplicity of the most likely macrostate is enormous. It's about 10 to the 16. And that this function drops quite sharply, such that even if you give 10 extra units of energy to QA, the chances of finding the system in that state has dropped by a significant amount. We characterize the shape of this curve in terms of its width, where the width is given by the number of units of energy divided by the square root of the number of particles multiplied by 2. And this is the value of X for which the value of the multiplicity has dropped by a factor of 1 over E, Euler's number. In this case, that number is about 8. If we take 50 divided by 2 times the square root of 10, that number is about 8. So our multiplicity has dropped off by a factor of 1 over E by the time we have given about 8 extra units of energy to QA, or given 8 extra units of energy to QB if we make X negative. And this tells us that if we look at this system in equilibrium, the chances that we would find it significantly outside of that range of QA is somewhere between, say, 17 and 33, within 8 of our central value, is very, very small. So what we would like to do next is we would actually like to change the values of Q and N and see how this multiplicity distribution behaves as we increase the amount of energy or increase the number of oscillators. Now we've doubled the number of units of energy that our two Einstein solids are able to share, so Q is now 100 instead of 50, while keeping the number of oscillators in each of our solids at 10. The first thing to note is that our multiplicity has gone up by an enormous factor, from about 10 to the 16 to about 10 to the 22. This is as expected because there are many, many more ways of rearranging 100 units of energy than there are of rearranging 10 units of energy. The other thing to note is that the width of our graph has also doubled because the width of our graph scales directly with Q. Now what we've done is we have added 5 additional oscillators to each solid. So n equals 15 now instead of 10. And again, our number of microstates, our multiplicity, has gone up by another huge factor. So we are now up to 10 to the 28th microstates in our most likely system, or most likely macrostate. One thing to notice here is that even while our multiplicity has increased greatly, the width of our peak has actually decreased. This is because the width of our peak depends on 1 over the square root of n, and so as we increase n, we narrow our peak. And in fact, what would happen in a large system, a very large system, would be that the peak would become so narrow as to be only a tiny fraction of the possible number of macrostates would be truly likely to occur because the narrowness of the peak would be so great. So here we have access, or the likely macrostates, say, lie between x equals negative 20 and x equals positive 20, which is about 20% of the total number of units of energy, right? The total number of units of energy is 100. If we had a very large system, something with a macroscopic number of particles, this would in fact not be anywhere close to 20% of the amount of energy in the whole system. It would be a billionth or a trillionth of the total energy of the system. Another thing to notice here is that adding 5 oscillators to the system increased our multiplicity by about the same factor as adding 50 units of energy. And this is a consequence of us operating in the high temperature limit. In the high temperature limit, it is much more beneficial in terms of total number of microstates to add a few oscillators to the system rather than adding a few units of energy. To think about why we gain more microstates when we add oscillators versus energy in the high temperature system, let's think about a single Einstein solid and see what happens when we add energy or oscillators. So we're in the high temperature range because we have more energy than we have oscillators by a decent amount. Again, these numbers are way too small for what we would really be thinking about. We would be thinking about 10 to the 23rd oscillators, etc. But at least this gives us some numbers we can work with to think about how this math works. Okay, so here we have the equation for the number of microstates for a single Einstein solid. And when we plug in these numbers, we get this value. We'll call this omega naught. And then what we're going to do is we're going to see what happens when we add 1 oscillator or 1 unit of energy. Well, when we add 1 oscillator, our numerator goes to 60 factorial instead of 59 factorial. And our denominator, our q factorial, stays the same, and our n factorial, or our n minus 1 factorial, bumps up by 1. We can pull the 10 out, so this 10 factorial looks like 10 multiplied by 9 factorial, right? 10 factorial is just 10 multiplied by 9 factorial. And if we do the same trick on top, where we realize that 60 factorial is just 60 times 59 factorial, we end up with this. So our multiplicity has actually increased by 6-fold when we add just 1 oscillator in this case. So now let's look at the adding 1 unit of energy situation. So now we still have 60 factorial on top, just like when we added an oscillator. But now instead of going from 9 factorial to 10 factorial, we go from 50 factorial to 51 factorial. And we can rewrite 50 factorial, or we can rewrite 51 factorial as 51 times 50 factorial. And doing the same trick on top, we get that this is 60 over 51. So, a little over 1 times the original multiplicity. So adding one oscillator increases our multiplicity by about 6-fold here, because we are 6 multiplied by the original multiplicity, while increasing our unit of our energy by 1 unit only gives us about a 20% increase in our total multiplicity. This relationship would be flipped if we were in the low temperature limit, where N was much, much larger than Q. That is, we have many more oscillators than we have units of energy. In that case, we would gain many more microstates by adding a little energy into the system rather than by adding oscillators into the system. As a small preview of what we will be talking about in the next chapter, this idea that if you add a little bit of energy, you gain a lot of multiplicity will actually turn into our definition in a way of what temperature is. That is, if I'm at low temperature, I gain a lot of extra microstates by adding in a little energy. And if I'm at high temperature, I gain relatively few microstates by adding in a little bit of temperature.